Hello, Honors Chemistry, and welcome to the back part of Chapter 8, where we take the exact same math that we started in the first half of Chapter 8, and all we're going to do is we're just going to throw in a couple of definitions that are going to make us be a little bit more thoughtful about how we do our math and how we approach it. So, thinking back to questions from the first half, right? One of the questions was, right, what is the same in all the problems? Like, what assumption are we making in every one of the problems we worked through 8.4. Right. The assumption is that we have enough of every other reactant, right? Our given is one piece of information, and we can assume that we have enough of everything else, right? Clearly, that's not how life works, right? Like your book goes through the example of pancakes, which is a good example, right? If you only have one egg in the refrigerator, it doesn't matter how much flour you have, you are limited by your number of eggs, right? Same thing like if you made sandwiches. If you only had 4 pieces of bread and limitless cheese, you would be limited to 2 sandwiches, right? Because that's what you need to make a sandwich, right? And the concept of a limiting reactant is exactly the same, right? Except obviously we're going to tie it into our math and mole ratios that we talked about previously. So first, let's go ahead and look at this concept check, because this is a really important one, right? Where here is where we are putting together the concept of limiting reactants and theoretical yields, but with particles, right? Which should conceptually be something that is really simple and really easy. First, let's go ahead and put some definitions up, right? Things that we should know, right? So first of all, we should know definitions of things like limiting reactant. Where what is a limiting reactant? Right, that is the reactant that produces the least amount of product okay, and another way to say that is if it produces the least amount of product, it is also the reactant that is completely consumed. Means that at the end of the reaction, there is 0 limiting reactant remaining. Yes? Does that make sense? All right. Next up, let's say that we also have, let's go ahead and define theoretical yield. So what's the theoretical yield? Right. That is the amount of product from the limiting reactant. Yes? All right. And then finally, let's go ahead and, while we're at it, let's go ahead and throw in percent yield. Right. That's the amount actual over your theoretical yield times 100, right? So great. Those are our basic definitions. Now, one huge important thing, when do we know to calculate a percent yield? When do we know that we should calculate a percent yield? Super important question. Right. Anytime we have amounts of both reactants. Okay, now that we've defined all those terms, let's talk about how to solve concept check 8.3. So, if we look, right, here we have our reactants, and if we look, we know the amounts of both reactants, right? We have 2 and 2, and we have 3H2, right? We could be talking in mole concept, right? Or particles. In this case, it's specifically particles. So we're going to go ahead and use these ratios in particles, right? So we have 2, what's the right word here? Right, molecules of N2, and we have 3 molecules of H2. So that meets this criteria, right? We know the amounts of both reactants, so we need to calculate a limiting reactant, right? So instead, in this one, we're not going to do any math yet, right? We're not going to do any written math. We're just going to think in our heads, right? So if we think about this, right, 3H2 will produce 2NH3, yes? 3H2 would produce 2NH3. 1N2 would produce 2NH3, right? So if we think about those ratios, which of these will we run out of first? Right, clearly this is our limiting reactant, right? In that for every one of these, there's an understood one there, we need 3 of these to produce 2 of those, right? That's what we understand. So I will use one of these and 3 of these. And what does that mean? Right. There is going to be 1 excess molecule. Yes? Does that make sense? All right. So then, if we're asked to pick which of these reaction vessels represents the end, right, what happens when we're done, that's what we need to look for. We need to find something that matches the fact that we used all of these, right, because that's what limiting reactant means we used all of that. We have 1 of my N2s left over, and we've produced exactly 2 of those, right? So if we look here, this reaction vessel A has nothing of my reactants left. That can't be it. This one has 1, 2, 3 of my NH3s, and it has 1 H2 remaining, right? That can't be it. Here, look, 2, which is exactly what we said, and 1 of my N2s. This is our correct answer. Yes? All right. Now, tying in some math with that. All right. So, Skill Builder 8.5 says we would like to know the maximum number of grams of NH3 from 25.2 grams of N2, 25.2 grams of N2, and 8.42 grams of H2, right? So again, we would look at this and we would say to ourselves, oh, look, we know the amounts of both reactants. Clearly, we must calculate a limiting reactant, right? Obviously, I'm not going to tell you that every single time because that's your job to understand that, right? That's what differentiates this problem from every other problem we worked in the previous section, okay? So, what's that mean? Right. What's that mean in terms of math is that we are going to start from each reactant and figure out which makes the least amount of product, right? Because going back to our definitions, the limiting reactant is the one that produces the least amount of product, which is also known as our theoretical yield. So that's what we're looking for. So we'll go ahead and start with our 8.42 grams of H2. Step 1 is to convert to what? Right, moles, because now all the math is the same stuff we've already learned. There's no new math here. We just pick up a couple definitions, right? So we know that for every 2.02 grams of H2, we have 1 mole of H2. And we know that for every 3 moles of H2, what's this conversion factor called? Right, this is our mole ratio, 2 moles of NH3, and for every 1 mole of NH3, we produce, well, it is equal to 17.04 grams of NH3. And let's go ahead and put the work out here for this next one, right? 25.2 grams of N2, same principle, we'll use molar mass. For every 1 mole of N2, and then for every 1 mole of N2, we could produce 2 moles of NH3, and then for every 1 mole of NH3, there are 17.04 grams of NH3. Okay, so that's all the work we would have to do, and we would find that from 8.42 grams of H2, we could produce a maximum of 47.35 grams of NH3, and from my N2 we could produce 30.65 grams of NH3. So here, let's talk about what that means, right? So that means from this amount we could produce that, from this amount we could produce this, but after we produced 30.65 grams of NH3, we would run out of N2. Yes, we would have consumed all of our N2, which means that this is not a real value. We can't actually make 47 grams. Going back to the sandwiches, that would be like saying we have boatloads of cheese, but not enough bread, so once we run out of bread, we're done, right? That's what this is saying in math, right? And note here, right, that even though this has greater mass, if once we take into account the molar mass, the number of particles, which moles is a measure of, is actually less, right? And that's the key here, right, is that it doesn't matter how many grams of it I have, we're going to have to break it down into how many of each needs to react together, right? So mass is not an appropriate measure. So anyway, this would then be labeled as our theoretical yield. Last, we would round it to 3 sig figs, right? So 30.7 grams of NH3 would be our potential yield, also known as our theoretical yield. Yes? All right, next up. So here, this one is more explicit. The reaction of 185 grams of Fe2O3, so 185 grams, with 95.3 grams of CO, so 95.3 grams of CO, produces 87.4 grams of Fe. What is that? Right, this is my actual yield. Okay. Determine the limiting reactant, theoretical yield, and percent yield. So, what's that mean? Right, same principle. We're going to start here, and we're going to go to Fe. We're going to start here, and we're going to go to Fe, and we're going to figure out which makes the least amount of product. All right, so we have our 185 grams of Fe2O3, and same thing as before, right? We're going to use our molar mass to get to moles. We're going to then go from moles of Fe2O3, so for every 1 mole of Fe2O3, we could produce 2 moles of Fe, and then for every 1 mole of Fe, that is equal to 55.85 grams of Fe. And let's go ahead and set up that second piece of work, which has that 95.3 grams of CO, which is 28.01 grams of CO for every 1 mole. Then what's the name of this next conversion? Right, mole ratio. So for every 3 moles of CO, we could produce 2 moles of Fe. And again, 1 mole of Fe for every 55.8 grams of Fe. Okay, so from our 185 grams of Fe2O3, we could potentially produce 129.36 grams of Fe. And from our 95.3 grams of CO, we could potentially produce 126.68 grams of Fe, which means what? Right. After we produce 126.68 grams of Fe, we would run out of this, which means this is not a real value. We can't actually make that much, right? So this would be my limiting reactant. This would be my theoretical yield. And then, last up, it asks for a percent yield, which means I'm going to take my actual, because percents are always piece over the whole, right? So my actual yield is the piece. My whole is what I was supposed to get, multiplied by 100, and that's going to give us our percent yield. Yes? Does that make sense? All right. Make sure you understand these things, and again, like your outline says, make sure you understand the definitions of limiting reactant and theoretical yield, and not just can you write it down, but that you grasp what they mean in the context of a problem. All right, other than that, make sure you finish your homework, be good, and I will see you soon. Thanks for listening. Bye.